So we've been talking about how you can understand a moment in terms of the twisting of the spanner around a bolt, where the force times the perpendicular distance is the moment if the force is at a perpendicular, or if you have an oblique force coming down through here, you have to divide that into its horizontal and vertical components and then work out the moments. And we know the horizontal component gives a moment of 0 because it's along the line of the moment arm. There is no perpendicular distance, and the vertical component we work out here from this oblique force. We can work out its perpendicular distance being the length of the spanner. Now, the most complex system happens when there's an oblique force acting on a spanner, and say it moves it slightly, so that now that the oblique force is coming through and it's not actually at a perpendicular angle to the spanner, but neither is the angle of the spanner nice and straight. So we haven't got any simple components. What we have here is this oblique has its own horizontal and vertical components. You see neither of them along the line of the spanner. Go through there. And the distances from each of these back to the spanner have to be understood. This one, this horizontal, has a perpendicular back here. And this this vertical, which has a line of action through here, will have its own perpendicular line back to the bolt somewhere up here. And we can draw that in terms of a system here. So in the system here, I've drawn the spanner twisting the bolt, and the spanner is at an oblique angle and the force is at an oblique angle. And as we said, this force coming down at the oblique angle has now got a vertical and horizontal components which have to be calculated. How do we calculate those? Well, we can imagine that this force is coming down through here. The easiest way is always to, if you can't see it any other way, draw a little parallelogram around the force, and you can see it has a horizontal component in that direction and a vertical component in that direction. And so you can then draw those out forever if you like, and you can see that this component here from trigonometry, if we know that this angle in here is theta, and we know that this is F, and we know that this force here is F cos theta, and we know that this force down here is F sine theta. So we've got the components of the force. Now we also need to work out the moment arms. So this is often the trickiest part, to see, well, where are the moment arms? If we've got an oblique force coming in here, been pushing on something, where are the moment arms? Well, you can see here this horizontal component, if you take its line of action along, you can find a perpendicular line back to a pivot point. So here you take the line of action along and you find the perpendicular back to the pivot point, and that is the moment arm for the horizontal force. And say you know what this angle here is, alpha, call that alpha, then we know that, and we know this distance here, d, well then we know that this horizontal moment arm is going to be d cos of alpha. And what is the distance for the vertical component of the force? Now remember, we're no longer considering the force itself. What we're looking for is the line of action for the vertical component, which is along here. Take it up, take it up, take it up, and then we find the perpendicular from that line of action back to the pivot point, and pretend that's the perpendicular there. Okay. If we know that's alpha, we know this is alpha. We know that this distance here from trigonometry is d sine alpha. So to work out the moment around the pivot point, the moment is, well, we can work out the vertical component, the force vertical times the distance vertical, and the horizontal component, the force of the horizontal times the distance of the horizontal. Okay, and we know in this case that the vertical component, we said the vertical component was f sine theta, and its distance, the vertical component, the horizontal distance back to the pivot point, was d sine alpha. And the horizontal component of the force was f cos theta, and its perpendicular distance back to the pivot point was d cos alpha. And now we just need to worry about signs. There's the pivot point. Anything going in that direction, in the counterclockwise direction, is positive. So we can see that the vertical component is positive, and also the horizontal component, which is also going around in that direction, is also positive. So you can see that in any system where you have an oblique force acting in an oblique plane, you need both the vertical and horizontal components of the force, and the distances from those components back to the pivot point. You look at the component and then its line of action and take the distance back to the pivot point. You don't anymore worry about the force itself. You've broken it into its components. So when you're working about moment arms, you're only looking at moment arms for its components. And you can imagine now that if you can understand this in terms of a spanner, that it has a horizontal and vertical component for any oblique force, and each of those has its perpendicular distance back to the pivot point. If you can use trigonometry to do that, then you can see that any system where you have obliques is similar to the system of twisting a spanner around a bolt. And if you can do this one, you'll be able to do it in similar types of systems.